Hi, it's Mark. I thought we'd review a few sections of Phil Halper's video called Black Hole Alternatives and How to Find Them. He has a number of scientists on in this video. I'll respond to a few clips.
This is the first ever image captured of a black hole. Theorists have begun to wonder if it really is a black hole after all. And if it isn't, what else could it be?
We are reasonably confident in Einstein's theory of general relativity, which would tell us that there are black hole solutions. However, if we were to assume that that was the only possibility, then we would be essentially dereliction of our scientific duty. So we have to look for alternatives so that we can see whether the black hole is indeed the right thing.
So the main idea for most of these alternatives to black holes are to get rid of the pathologies associated with black holes. Most significant one is the singularity at the center. We don't know what to do.
So I wanted to talk about that singularity. There are no singularities in black holes. There's no singularities in the universe at all. The problem here arises because they're just extending Einstein's mathematics without realizing how Einstein's space-time is implemented. The reason they don't understand that is because they're just working with Einstein's math and there's no foundation underneath that. Likewise, in quantum theory, they have no foundation underneath quantum theory. Both of these theories work fine in today's context. Sadly, there's a lot more to know that's actually fairly straightforward to understand, but it was missed 125 years ago during the classical to quantum transition. And there's a neoclassical solution. It's not a classical solution, but it's very simple and straightforward. The basic idea is that nature is implemented with point potential particles. They are true geometric points with no radius, zero radius, but they constantly emit potential at a constant rate. And it turns out with 6 point potentials arranged as three binaries, three orbiting binaries. So each binary being one positive and one negative point potential. These point potentials can form assemblies. So with this triply nested binary that forms in black holes, you have a structure that is the nucleus of every standard model particle. Sometimes these triply nested binaries are used more than once in some particles, like a photon has two. Space-time and fermions each have one Noether core. I named these nuclei, these triply nested binaries, after Emmy Noether, who did a lot of work in this area. So it seems fitting that this assembly should be named after her. One of the interesting properties about these binaries is that there is a maximum curvature. You cannot go beyond a certain minimum radius, maximum frequency, and maximum orbital velocity. And that's due to the geometry of the binary. In a little more detail, when these Noether cores, these triply nested binaries, reach the event horizon of a black hole, that's when all of the orbital velocities are at field speed, and the event horizon corresponds to the Planck scale. Inside the black hole, that's the deflationary, inflationary region, what we would call anti-de Sitter space. Proceeding into the black hole towards the core, these Noether cores will get smaller and smaller and smaller with faster frequencies, faster orbital velocities until they just reach their limit. And that's why there's no singularity.
The other one is basically how black holes evaporate and lose their information. These alternatives don't necessarily do all these things. I mean, certainly you want to get rid of the singularity because that's the one that makes the least sense. But whether these things evaporate the same way that Hawking predicted, that's also not clear.
I just want to point out here that Hawking evaporation again is kind of based on the general relativity mathematics, but it's really just a minor outflow from black holes. The major outflow from black holes is fresh new space-time assemblies, and they just fly right through the event horizon. While you have things going into the black hole, this is a recycling universe. And so when they reach their ultimate energy, then they may start the journey out. And that's the inflation part of what we call the Big Bang, except it's not a Big Bang. It's not a one-time event 13.8 billion years ago. What we call the bang is inflation inside of a supermassive black hole, the escape of these Noether cores that are extremely high energy, extremely tiny, extremely difficult to detect. They then go on and expand once they're outside of the black hole. So that's where expansion comes from. Inside the black hole is inflation, deflation. Outside the black hole is expansion, contraction of these Noether cores. And when they come out, they're so high energy, they start expanding. And so the space around the black hole, which is these assemblies, as they spread out, they dissipate energy to other space-time, to other particles, and they grow. Orbital velocity drops, the frequency drops, the radius increases, so they grow. This will be a new solution to galaxy rotation curves. It's a new solution to dark energy and dark matter, which has been long sought after. But my main point here, responding to this scientist, is that there's a lot more escaping a black hole than we realize.
Basically, the main motivation is that these pathologies that exist in standard classical black holes, you want to basically undo them one way or another.
We have these particles that tend to be characterized as either fermions or bosons. Fermions are more or less are building blocks, things like the electron or the proton that makes the nucleus, whereas bosons are things like the Higgs boson, like the photon, the particle of light.
So I'm not sure the Higgs is properly classified as a boson. The reason it's undetectable basically has three reasons. One, the frequency of the Higgs is so high that it's well beyond our ability to measure frequency. One other aspect is that point potentials are constant rate emitters. So the faster they go, the less potential they emit at each point along their continuous path. So the expanding sphere of potential has lower magnitude as it is first emitted and as it expands, and the normal fall off we see in potential is 1 over the radius of that expanding potential sphere. There are aspects of these Noether cores that come out of the black holes that make them very, very difficult to detect. I don't know if I would call them bosons. I mean, maybe they are. Maybe they're very flat when they come out of the event horizon. But it's more than just like saying they're bosons. It's understanding that the graviton is the first generation of a space-time assembly. If you destroy the outer binary, in these triple binaries that make the space-time, if you destroy the outer binary, then you get a Higgs. All right. So it's just kind of like fermions, they have generation one, two, three, so like electron, muon, tau. To go from an electron to a muon, you have to take away the outer lowest energy binary. And that reveals the higher energy muon inside of a electron. If you take away the second binary, that's going to reveal just the last binary, which is the tau, which is extremely high energy. And so same thing in the other fermions, the quarks. It's really difficult for these scientists to make progress because they're on the wrong ontology. And by wrong, I mean, yes, general relativity and quantum mechanics kind of work, but there's so much more to learn. And if we had been on the right ontology starting 125 years ago, we'd be so far past where we are now that it's incredible. Like these scientists, they don't understand what a graviton is. They really don't understand a Higgs that well, except maybe mathematically. They think that generation one, two, and three of the fermions are like completely different particles, but actually they call them particles in one aspect, but then they also model all the standard model particles as fields. So just a field. But that's not correct. There's only one field, and that's the potential field. And what they think are the fields that describe a unique particle is the emissions of one of these assemblies. And so an assembly, like a fermion assembly, has 12 point potentials in it. There's the 6 in the Noether core, and then there's 6 personality charges decorating the Noether core in the axial poles. These things are very difficult to crack open. We have to use a huge particle collider to, crack open the binaries. We don't often see, or I don't think we see at all, the case where the point potentials that are the personality charges fly off, right? We have never seen an electron with 5/6 of a electric charge or 1/6 of electric charge, indicating that, just a few of the personality charges remain. So I don't know that they can really ever have a breakthrough until they go back and find out what was missed or what wasn't observed around 1900. They only tried one very primitive point charge model at 1900. They said a negative point charge could be an electron, and a positive point charge could be a proton. They tested that, and they falsified that idea. And then they set aside point charges or point potentials, and as if that was the only model that could possibly exist of point charges or point potentials. Well, there's infinite models that could exist, right? With different physics, different charge or potential magnitudes, um, you know, different ideas in terms of how they move. Do they move continuously? Are they operating inside of Einstein's geometry, or are they operating at a lower level in a Euclidean void of 3D space and time? That's actually what they are operating in, is the Euclidean void. And so these assemblies are what creates space-time and what creates all the rest of the standard model particles.
The boson star is that if you have a type of a scalar field in the universe which is very light, so the only scalar field that we know exists in the universe, which is fundamental, is Higgs field, but it's a very, very heavy field. But you could imagine fields that are very light, so much so that the Broglie wavelength of these fields is very big, size of what a black hole would be. We haven't seen any such light particle. The lightest particles we've seen are something like electron or maybe even a neutrino, but we need something much, much lighter than electron or neutrino. But if this kind of fields exist in the universe, they could form structures that are compact, that look like a black hole, but not quite as compact as a black hole.
One of the tricks of nature in its house of mirrors is that these Noether cores use superposition to shield themselves. They don't reveal much of their internal energy at all. Depending on the frequencies of those 3 binaries, they are going to superimpose their potential fields, and you just won't have a lot of energy escaping. And, of course, we convert apparent energy to mass, while science doesn't really yet understand the shielded energy via superposition. What the scientist is saying here is they're looking for a super light particle. Well, they know about the Higgs, that's heavy. They don't know about the next generation at higher energy inside the Higgs, which is incredibly high energy. And they also don't know about generation one, which is the full triply nested graviton. So it goes graviton generation one. If you were to knock off the outer binary, then you get Higgs. And if we had the enough energy in our colliders, we could knock off the second binary and get to, I don't know what you want to call it. It's just a raw binary at incredibly high energy. Of course, this solves the vacuum catastrophe, if you've ever heard about that, which is, why does the physics calculation of space-time energy, why is it like tens or dozens of orders of magnitude higher than what we observe? And the reason is because they're shielded, right? They're like stealth. Also, I think, although, a lot of this is my intuition and logic, I believe the Noether cores that make space-time kind of nestle together. So that also kind of shields the potential swirling in their poles. So that's another possible reason they appear even lighter and even less interactive. But those are the things that create gravity because they change shape around apparent energy. So if you're next to a fermion, or it's going to have relatively high energy, those gravitons are going to absorb that energy and deflate. So that's creating a gradient in the graviton sea or gas, if whatever you want to call it. That gradient is part of causing gravity because fermions will tend to follow that gradient, packing in closer and closer together, right, with gravity. Also, as mass gets denser and denser, there comes a point where the space-time assemblies, the gravitons, start oblating. So instead of being, kind of an approximate spherical path on the outer binary that's kind of precessing all around this little assembly, then they will start becoming oblate spheroids as they get towards denser and denser mass, including eventually, if they're going fast enough, I would believe they will become planar. And that might be like in the event horizon of a black hole, or like a photon is, I believe, planar. It's actually two Noether cores, one pro and one anti, contra-rotating. And I think they're both planar and they're offset by a little bit. And that would explain all the behavior of the electric field we observe out of photons. We can explain polarization and so forth. It's kind of different than what they're imagining because they're on the wrong ontology. Let's go on.
Gravistar is an interesting and kind of old idea when I was a student, actually, back in early 2000. And it has to do with the thing which is kind of interesting about the nature of the black holes, that the universe with a dark energy, which we seem to be observing, seems to pushing everything out. Everything is moving away from the center. Black holes are sucking everything in. What if inside of the black hole is like the black hole inside out, which is like our universe, which is filled with dark energy?
Again, confusion. Inside the black hole is the inflationary deflationary region. It's what we call anti-de Sitter space. They think about everything being sucked into a black hole and not much being emitted, just Hawking radiation. But as I explained already, what's coming out of there is very high energy Noether cores. I don't know exactly how they're configured. Are they coming out flat like a boson? Are they coming out like a dark photon? Or they just kind of come out like little tiny bullets that fly all over and eventually expand and maybe interact to create new standard model fermions or photons or neutrinos, quarks, electrons.
What you have is sort of your normal black hole type of, outside the object. But instead of just carrying on with the same sort of Einstein type Schwarzschild solution, it's called, this black hole, you have a shell of some form of matter. And then inside it, you put, and this is going to sound really bizarre, you put what we would call an expanding universe. If you think about it, the black hole kind of wants to suck things in. So if you want to fight against that sort of being sucked in, maybe an expanding universe is kind of the obvious thing to do.
Yeah, they're close. It's like so many theories here in physics. Nobody's really totally wrong. Everybody is detecting something in the mathematics or the observations that appeals to them and suggests some kind of a behavior. And so in this case, the scientist is talking about, well, maybe inside the black hole is kind of an expanding aspect inside the black hole. What they don't understand is that that's really the inflationary region, because they've got the inflationary region assigned back to the Big Bang, which didn't happen. We're living in a steady state universe, And you can think of the Big Bang as being just a distributed bang throughout all time that comes out of black holes, particularly supermassive black holes, so that we just kind of recycle matter and energy. Whatever matter energy is in a galaxy is going to kind of tend to stay there, recycle into matter that clumps and eventually joins, a planet and eventually joins a sun and eventually goes supernova, whatever. And then there can be places where you get neutron stars and small black holes. And of course, in the center, you're going to have that supermassive black hole. And you're going to have all that space time that inflates inside the supermassive black hole, escapes, and then continues expanding from there. In terms of the binary, what's important at the event horizon of a black hole is that it's the border between anti-de Sitter space and conformal field theory. So inside the black hole, the binaries have an orbital velocity of the 2 point potentials in that binary greater than their own field speed. So that means their own shadow of where they were before on their path is acting upon them. So inside the black hole, they're going to deflate really fast because not only are they kind of getting a signal from their partner, kind of a delayed signal from their partner across not even the diameter of the binary because it's delayed, they're going to get the potential from their partner along a chord of the orbital. But if they're inside the black hole, they're also getting a strong push from their own self because they're ahead of their own potential emission, and their previous potential emission looks just like themselves. Therefore, it's a like particle, and like particles repel. So this is the two regions. Outside the black hole, they're moving less than field speed. And so the only action they're getting is from the potential emitted by their partner. And that's why there's two regions. And the event horizon is the symmetry breaking point between those two regions where the point potentials are moving at field speed. So they're just keeping right up with their own field. So again, it's just so confusing. Nature is so self-similar in so many ways. The black hole, in a sense, emulates the behavior of a Noether core, right? Basically, the smallest nucleus of the universe, these triply nested binaries, is really kind of a model for how a black hole works, right? Because in a triply nested binary, what I think happens is the middle binary somehow tends to operate at field speed, and the outer binary operates at less than field speed. So it's like agreeing with conformal field theory. It's kind of in the expansion contraction region of a binary. The inner binary is going faster than field speed, and that's in the anti-de Sitter inflation deflation region. In these triply nested Noether cores, they tend to be, if they're in the right kind of particle, the right kind of assembly, they tend to be relatively stable. Like, so if they're in a proton or an electron or photon, neutrino, they're relatively stable. In a neutron, for some reason, which we'll find out, they aren't all that stable. They would kind of decay if they were on their own within about 14 minutes. Nature is often self-similar. This idea out of fractals of self-similarity at different scales, this idea of the binary orbitals in the triply nested Noether core. You've got planets orbiting the sun, moons orbiting planets. It's kind of like everything is crying out to us. Find that thing at a lower level in the ontology that behaves like these effects we're seeing at larger scales.
And so specifically what they put is this particular form of an expanding universe that cosmologists believe happened in the very, very early universe.
Right. This is a great picture. You can see that inflation regions, right? So all the way to the left of the diagram, you've got the quantum fluctuations, and then you have the very rapid inflation. And that, if you kind of look at it, the curvature of that shape is anti-de Sitter. It's bending over to the right. The slope of that curve is getting less as it proceeds towards the event horizon. Then they show the cosmic microwave background there as that little blue and green and with some orange specks. That's supposed to be the cosmic microwave background. And they say it happens after 375,000 years. In terms of the Big Bang, which is wrong, what that really is, very close to the event horizon. And beyond the event horizon, you see that the slope's reached a certain point, and now it's going to increase slightly as it goes on. So those are two very different regions.
In inflation. So it's a very special source. It's something which we call the cosmological constant.
So the original idea of gravastar was basically inside of the black hole, instead of a singularity, an empty space, you actually have type of dark energy that pushes everything out. And you have some sort of a surface, some kind of a surface. So it is like a star because it has density in it and it has a structure. It is a very weird star. It's a dark energy star, and it has this weird membrane that separates the empty space from this dark energy space.
All right, this is fascinating. What he just said, right, is that on the outside of a black hole, that would be empty space. But it's not empty space, right? It's only empty space if you think of it from the point of view of Einstein's general relativity, and you're just looking at the mathematics. But Einstein's general relativity expresses no implementation of how nature does that. And so I think what has happened to a lot of physicists is they've kind of just talked themselves into this idea that this geometry appears out of nothing. Einstein's geometry just appears out of nothing. And so he calls it empty space. It's not empty space. There is no pure vacuum. And if you look at the other work out of physicists, they'll assign all kinds of things to space-time, right? They've got the quantum vacuum, which is a Roiling vacuum. They've got pair production of new particles. They've got particle annihilation going in. It's a really strange way they're looking at it. To them, the mathematics is all self-consistent, and so that's why they think they're on a firm foundation, but they're absolutely not.
So outside would look like a black hole. Inside is this dark energy universe. Looks like a universe filled with dark energy. And then there is this membrane that separates them. And then exactly where this membrane sits would tell us like how different from a real black hole or a general relativity black hole it looks like. So if the membrane is very far out, then it would be probably very different from a black hole. You could see the membrane and its properties. If it's very close to the horizon or inside the horizon, then probably we won't be able to tell the difference. But then also, it would be hard to see how a membrane could sit inside the horizon. It would be a very weird membrane.
The whole key to solving the black hole puzzle was that in string theory, the objects are not point-like particles which can race around the way we always thought in particle physics. They are like strings and brains, which are what we call extended objects. They have a size.
When he talks about point-like particles, he's not referring to point potentials that I'm talking about. The physicists still think of the standard model particles as point-like, so an electron is point-like to them, because they don't think they can divide an electron, although they don't realize that when they make muons and taus, they're actually breaking part of the electron and destroying part of that Noether core triply nested binary. So just keep that in mind. Different kind of point. Their point is vague due to lack of understanding of the structure of their particles. Mine is the point potential, which is, I'm saying, a fundamental particle in the universe.
So the reason the black hole puzzle was solved is that anytime you try to make a black hole out of point-like particles, they all rush to the middle the way everybody thought. But if you put energy in a string, it can go into two places. You can make the string move faster, just like a particle, but you can also put it into stretching the string. And there are many more ways to stretch a string as compared to just moving it. And so just on the laws, based on the law of thermodynamics, the energy actually goes preferentially towards stretching the string. The guy becomes so big that it becomes this fuzzball, and that's how the puzzle was solved.
Every theory, things like string theory, it's just a huge, incredibly intense set of mathematics. And again, I look for similarities in ideas, and sometimes I wonder if string theory is picking up the hints of the paths of point potentials, depending on their velocity of the point potential. There's a history there that where potential has been emitted and it's still expanding at field speed. And so sometimes I wonder if like that's the echo that they see in terms of string theory, in terms of trying to make it work. But they would be a lot better off if they switched to point potentials and the paths of point potentials through continuous Euclidean space and absolute time.
Now, the idea of Planck's stars is that at some point when you get close to forming a singularity, then you have some quantum effects that turn things inside out. So your crushing basically singularity becomes a banging, like a Big Bang singularity. And then out of that, you make a white hole. Basically, you form a black hole or something very close to the black hole, wait for a while, and at some point it explodes. And it's called Planck stars because this presumably happens sometimes around when you get close to a Planck density.
This is really interesting. He's saying that as you get close to the black hole, enter the event horizon, and then get close to the singularity, that you would be approaching Planck scale. I see this very differently. I think Planck scale is going to be reached around the event horizon, which is where the Noether core triply nested binaries should all reach field speed and their orbital velocity. So then inside the black hole is your deflationary region as you're moving towards the center, which is not a singularity. When you hit that and reach the highest energy, then the Noether core is ready to turn around and blast out, which kind of corresponds to their white hole here, except it's the same direction, just reversing course, going out of the black hole. It's a very different idea, and I don't know what that scale would be. That scale is opaque to us, so we're going to have to figure it out mathematically. But if Planck scale is near the event horizon, we know that whatever scale this is down near the core of the black hole has got to be incredibly small, incredibly high velocity, incredibly high frequency. That's fascinating. But again, you see these echoes, right? You got the black hole and the white hole. So white hole is like, they'll say things, I don't know if these physicists will say it, but some articles and writers say, oh, the white hole, might show up somewhere else in the universe, right? Or maybe there's a wormhole between these two things, and it's like it's not that exotic. It's just you know these Noether cores, the triply nested binaries, got totally energized up on the way in, and now they're ready to proceed out and back into the galaxy to create fresh high energy space-time, which is going to expand once it's outside the black hole. Everything makes sense.
Out of that, you make a white hole. Basically, you form a black hole or something very close to the black hole, wait for a while, and at some point it explodes. And it's called Planck stars because this presumably happens sometimes around when you get close to a Planck density. So there's the transition from black holes to white holes.
This is where you need quantum gravity, because the black hole shrinks to a very teeny size. It shrinks till it reaches a minimal size at the Planckian length. So there you definitely need quantum gravity. And loop quantum gravity provides concrete calculations to know what's going on there. It solves the problem of what happens in the interior, because you don't have a singularity anymore. Quantum gravity cures it, but also it tells you what happens in the exterior. So the final objects really behave as a quantum particle in a superposition of a black and a white hole, just like the Schrödinger cat that is dead and alive. Here, our particle is both black and white, and is just a stable object stabilized by quantum effect that lives very long.
Planck stars are a candidate not only for black hole alternatives, but also for the mysterious dark matter that is believed to pervade the universe, which physicists still haven't identified.
What's being said, it's a stable particle, which is true. Noether cores are long-term stable. In their metaphor, they do kind of change on the interior from a black to a white shape, right? So if you consider black is on the way in and then white is on the way out, it's essentially the same type of particle. It might not be the exact same point potentials. Maybe even the binaries decay as you get closer and closer. And then this is just a natural formation of forming binaries and forming nesting of binaries, so that by the time they get back up towards the event horizon, they're either some incredibly tiny Noether core that just shoots out at high velocity, or maybe they're like a dark photon, a photon with frequencies higher than Planck scale. And so we wouldn't necessarily be able to detect them until they had redshifted down into the conformal field theory area where their velocity, orbital velocity falls below field speed. Maybe if these are dark photons emerging out, maybe something interesting happens when they reach field speed. Is that a place where they're more reactive, or they may somehow interact with other space-time to create, cosmic microwave background photons, or create a little particle shower that creates protons and neutrons, so you might get hydrogen and helium atoms. I mean, these are all new things to explore because it's a new ontology, and we have to figure out how this all maps to general relativity and quantum theory. Those theories are fairly decent, but they're at the wrong level. And we just have to figure out, they're a reference model now. So we have to figure out, how do we map to those reference models? And then what do we do with them? Can we reframe them without throwing them out? Can we just doctor them up so they'll be functional? Or is there a whole new way to do the mathematics and the modeling and the simulation that's going to be superior in some way? I think in many applications, using simulation of point potentials and their paths has got to be very easy to deal with from a simulation, like time-based simulations. And you could do all kinds of mathematical techniques for, to handle different speeds of particles efficiently. So we're going to learn a lot more. All of these ideas are, decent ideas from a confused ontological standpoint.
So in loop quantum gravity, we may have ways in which this scenario can turn as something concrete, and not just for big primordial black holes, but also for very, very teeny one, as loop quantum gravity allows for small black holes to turn into remnants. Quantum objects that have just the Planck size, namely the mass of a particle that is just Planckian, but very, very teeny, having the area that corresponds to the Planck area, the minimal possible area in the universe. So these objects are just the perfect dark matter.
With these and other alternatives to black holes, the question remains how to distinguish them from the classical black holes of general relativity.
It's the million-dollar question, isn't it? I mean, it's kind of frustrating because the black hole itself, by that event horizon, that sort of horizon between what we can see and what we can't, sort of almost by definition, you can't get there to touch it or to measure it or to see it, because it is, by its own definition, there's something we cannot see behind. So instead, what we have to do is to look for the implications.
The implications of black hole physics should be revealed by gravitational wave observatories like LIGO and its successors.
When you have two black holes that sort of are in one of these, what we call a binary system, i.e. there are two orbiting objects. For example, in our solar system, we've got the sun and we've got Jupiter. It's quite common to have two large astrophysical objects. Now, if these two just happen to be black holes, then eventually, they're orbiting, they're spinning around each other, they're slowly emitting these gravitational waves, and very gradually they spin towards each other and then they merge.
I'm just going to pause there to say, this is a binary at enormous scales, right? Jupiter versus the sun, that's already fairly large binary. They're slightly different. But then you get into neutron star binaries and now black hole binaries. Again, nature is often self-similar, right? That's right there, three different kinds of binaries. I'm talking about a binary as a scalable assembly that goes from way below the Planck scale to the Planck scale to larger. That is going to be the most primitive assembly that's possible, is a binary, right? Because if you have two point potentials that are the same polarity, they're going to repel, right? So they're not going to make, just the two of them aren't going to make an assembly. They're going to just fly apart. But opposite point potentials, a positive and a negative, do form an assembly. And that's the smallest assembly. There's only 2 point potentials. What else And there's only one way to form that assembly, which is an orbiting binary. I mean, yeah, they could pass at a large distance, but if the universe was empty, they would eventually orbit, maybe at a very large radius. The other thing is, if you look at this picture that's being shown of black holes, and you see kind of the spiral pattern, that's very self-similar to the spiral pattern of potential that emerges from a point potential binary, except this is at some, enormous scale, right? And the what a gravitational wave is kind of the energy and displacement of the space-time that these black holes are swirling up, right? Because you can get frame dragging, which means they're so dense, they're actually dragging some of the space-time with them, and they're disturbing that space-time. And that compression wave will just proceed through space-time near the black hole and just keep expanding out. And it's kind of a quadrupole wave, which means, remember, these noether cores are kind of like oblate spheroids. So if you hit them with an energetic wave from one side, it's going to be other space-time assemblies kind of pushing against you, which means you're going to kind of squish even more oblate, and then you're going to bounce back, and then you're going to kind of ring out. That will just keep proceeding. And, here we are, hundreds of millions of light years away, and we're picking up these waves with our various LIGO instruments around the world, which is fascinating.
That is a very violent event, and it sends this massive burst of gravitational waves out across the universe. Right near the horizon, gravity is so strong, at least for most astrophysical black holes, that it would rip us apart and be physically impossible to, say, send a probe down to explore.
That's exactly right. Fermions would be destroyed on the way towards an event horizon. I'm saying the only thing that could probably reach that would be noether cores in a flat planar state, which would be like photons, or just as these noether cores are left after the fermions decay, those noether cores would reach a flat planar state.
So what we end up doing is looking at the predictions, looking at what Einstein gravity tells us, and we ask, well, what happens if the black hole sucks, let's say, some other star or material that then heats up massively so that it starts emitting all sorts of light? How would that light travel to us? What would it look like? And so that's one possibility. And that is behind what the Event Horizon Telescope did to observe the shadow of a black hole. So we can't see the object itself, but we can see the shadow that it puts between us and this, light behind it, or emission from things that are being sucked in.
Remember, in the model I'm working on, the point potential model, space-time is made out of point potentials, these noether cores that are extremely high energy, extremely lightly interacting, and they permeate everything. They would even permeate the space between like an electron and a proton, or the nucleus of an atom. And then photons are traveling through this space-time. And photons, in my opinion, are made of two contra-rotating planar noether cores. All of our observations, well, almost all of our observations until just very recently, are based on photons. And yet science doesn't understand what a photon is, and science doesn't understand how space-time is implemented. So needless to say, that's going to change how we interpret photons that are traveling to us from billions of years away, and how they redshift through space-time. Because of the wrong ontology, even the interpretations here are going to be confused. They think that the redshift is due to the universe expanding, when in reality, the redshift is due to space-time expanding, but that's because space-time is generally expanding everywhere, right? It came out of the black hole as super high energy, and as it moves through the galaxy and out of the galaxy into intergalactic space, it's dissipating energy, right? And so all photons will be passing through space-time that is to some degree expanding. So the discussion of all these topics in this video has caused me to have a new potential insight, brainstorm. We talked about how Noether cores out in deep space would be essentially spherical because there's really not much gravity there. And as they get towards heavier and heavier mass, they'll get smaller and more oblate. I'm showing that in this chart, going from deep space on the first row to a star surface. These are just conceptual figures. And then as we continue moving towards a black hole, we're getting more and more oblate, smaller and smaller radii of the orbits, but we still have the orbital velocity is less than field speed. And the idea is that when the Noether cores reach the event horizon or that area, they're essentially in a planar state. And we say that about photons as well. And we also say that time kind of stops in Einstein's spacetime at the event horizon. So that's really interesting. It's like the oblateness of these orbital paths has something to do with how we perceive time in Einstein's spacetime. And so that's interesting. But the new insight I had is, well, maybe inside the black hole, this rotation of these orbital planes just kind of continues through the symmetry breaking point, that planar state, and keeps rotating, but now it's the other way. And why I think that's interesting is because you often read that inside of a black hole, time might run backwards, right? So people are somehow seeing something in the math, right? It's like time is slowing as we get to the black hole. What happens inside? I don't know if it's just a logical leap or if it's something in the math, but some people say time might run backwards. If that's the case, it's not really backwards in the sense of absolute time, because absolute time is an abstract concept that just moves forward linearly. But in terms of the way Einstein's time is perceived, the orbital planes continuing to fold and then open up on the other side, it might flip the math so that we would perceive it, or there would be some sign in the mathematics that would cause us to think time is running backwards. Of course, it's not, but it's an interesting thought. And then by the time the Noether core descends into the very center of the black hole at the core, perhaps it's reached another spherical state. It's very tiny, just kind of nestles right up there and joins into the core. And the core, of course, has just one microstate and zero entropy. From the perspective of the physics of the black hole core, the point potentials aren't moving relative to one another. All right, so that's it for this video. I really appreciate Phil Halper and the scientists that were in his video. When they do that kind of outreach, it helps me because it gives me something to compare and contrast with the new model I've been working on. So I hope this was interesting. I'll try to find some more subjects to talk about in future videos. Thanks.